the usual cohomology. So comparison theorem holds. So let F be a map of schemes which is separated of finite type over K. Then we have a commutative diagram as I wrote yesterday. And if we assume that F is torsion, for torsion sheaf F on X at, then we have an isomorphism of in derived category. So we have the natural base change map and this is isomorphic. So, as I explained yesterday, this type comparison theorem implies the comparison of cohomology. If we put y equal to super k, so let X be a scheme separated of finite type over k, and F be a torsion sheaf on X. Then the compactly supported cohomology of F is isomorphic to the compactly supported cohomology of its analytification. So we can compare it. We can compare them. Yeah, very nice comparison. And actually, it is easier to deal with cohomology of compact support than the ordinary cohomology, because we have some excision exact sequence, so we can patch or cut schemes freely. So it is easier to treat and prove this theorem. And there is also no finiteness result, which is slightly better than the finiteness for ordinary cohomology. So let K be a separably closed non-Archimedean field, and X be a separable rigid space, separable quasi-compact rigid space over K. And N an integer which is invertible in K sac, and F to be a constructible Z over NZ sheaf on X. Then we have the finiteness of this cohomology. yesterday I explained a similar theorem, but then we need the assumption that the characteristic of k is equal to 0 or something, or x is smooth. But for compactly supported cohomology, it is known that it is always finitely generated. Yes. Actually, I don't know the exact reason, but yeah, it is proved by Huber.
Nearby cycle?
Yes?
Algebraically define nearby cycle or define with analytic concept?
Which one?
Arc side.
Oh, that is algebraically defined nearby cycle. But we can define it analytically because we know they are isomorphic. Yes. So yes, we only consider the case our x comes from algebraic setting. Okay. And I don't know whether this type comparison result holds for general periodic x and replace it by analytic nearby cycle. Okay. And the final property is the Poincare duality. We have Poincare duality between ordinary cohomology and the compactly supported cohomology. So let K be a separably closed non-Archimedean field as before, and X be a purely d-dimensional rigid space over K, which is separated, smooth and taut over K, and N be invertible in K sac, and F is a locally constant V over NZ sheaf of finite type. Then we have a Poincare duality H2D minus I X F dual D is isomorphic to HCI XF dual. For ordinary cohomology is a dual of compactly supported cohomology. Yes, okay. This is the theory of compactly supported cohomology. So, and I will mention a bit about erratic cohomology. So far we only consider the torsion coefficient. But to apply it to number theory, we need erratic, to extend it, erratic cohomology. I will explain how we can define erratic cohomology. So the final section is L-adic cohomology. Actually, there is no good L-adic cohomology for ordinary cohomology. But for compactly supported cohomology, there is a good theory. So I explain it. So we want to consider something like VL or HCI X QL, which is defined as VL tensor QL or QL bar if you prefer. How to construct it? So usually some people want to take just an inverse limit of the torsion cohomology, but it is not the true, correct construction if X is not quasi-compact. So I introduce a correct definition. So consider the functor. So the definition is as follows. So consider the category of consider the category of systems. So projective system of sheaves. Fn such that Fn is Z over Ln plus 1Z module. So consider the category of projective system of sheaves. It is known that this is Arbian category with enough injectives. And from there to up, this is just a functor which assigns Fn to the inverse limit of yes, so yes, just X Fn. So let me consider this functor and take the take the right derived functor of this functor. And if X is partially proper, then HCI X Fn to be the ith derived functor of it. Defined as a ith derived functor, and if X is general, then we define it as by using universal compactification, 0 star Fn, where J from X to X bar is the universal compactification of X. This is the correct definition. And then if X is quasi-compact, X is quasi-compact rigid space over K, of course separated as taught, then it is known that HCI XZR is K is the separable equals, then it is just the inverse limit of torsion coefficient. And if X is not quasi-compact, say rigid space over K, which is separated taut, then HC I XDR can be computed as the inductive limit of U, which is a quasi-compact open subset of X. So the important point is the order of this inductive limit and this inverse limit. If we just take the inverse limit on there, then the inductive order of inverse limit and the inductive limit changes. And it makes this cohomology very complicated one. But it is a true definition. Okay. So finally, we get Galois representation from the rigid space over local field. So let K be a complete discrete variation field, and let X be a rigid space which is separated taut over K. then we get the cohomology xk bar QL, which is defined as a tensor product. And there is a natural Galois action on there and there. And we know that the action is continuous. It is not. It is probably automatic because the inertial group is finitely generated. But yes, we can prove that the action is continuous by using these properties. And if some periodic group G acts on X continuously, I didn't define the notion of continuous, but you can imagine it. I hope it. Then there is a natural induced action on this space, and this action is smooth. Namely, every element has an open stabilizer. So we can get nice or appropriate. So yeah, okay, nice representation. Yes, this is the end of my lecture. Thank you very much.